Now let's do an example, actually two examples of a one sample hypothesis test, and then we will get into the p-values as well. Okay, so let's get to a whiteboard. Maybe we'll keep this. Okay, so let's suppose that we work for a car company. Okay, work for a car company, and we want to know. We just invented. We work in our electric vehicle line. Okay, and we just invented, or think we invented, a rechargeable car battery that fully charges in only 3 minutes. Okay. We think it takes 3 minutes to charge, right? It's just as fast, if not faster, than filling up with gas. Okay. So at our car company, we just invented a rechargeable car battery that fully charges in only 3 minutes. We want to know if it is reasonable to think that our our new battery charges in only 3 minutes. Okay. We want to know if it's reasonable to think that this battery charges in only 3 minutes. So, what would we do? Well, before you're going to launch this new car battery and put it out on the market and say to everybody on commercials, hey, we have this new car and the battery, it charges in just 3 minutes, even faster than filling up with gas. So, come and buy it. Just plug it in, listen to a song, and your car is fully charged, ready to go, right? Well, we want to know if it's reasonable to think that our new battery charges in only 3 minutes. You're not going to just go out and start selling this car and marketing it. You're going to test it with a sample first. You're going to take a sample, see how long it takes to charge, and then you'll try to figure out if this is representative of the larger population. So, we want to know if it's reasonable to think our battery charges in only 3 minutes. So we take a sample of, I don't know, let's say 11 batteries and discover that on average, they charge in 2.85 minutes with a standard deviation of 0.42 minutes at the 0.05 level of significance. Is it reasonable to believe the new car battery charges in only 3 minutes. Okay. So what should we do, right? This is a one sample hypothesis test waiting to happen, right? It's a one sample hypothesis test waiting to happen because we want to know if it's reasonable to believe a hunch, a thought, a suspicion about a population and how it relates, right? How it stands against a specific value, right? We want to know if this population of car batteries really does take 3 minutes in order to charge. So what we want to do is we want to know if our suspicion, if it's reasonable to believe what we think we know. Okay. So what's the first step? First step, state the null and the alternative hypothesis. Okay. What's the null and the alternative hypothesis? Well, we want to know if it's reasonable to think that this car battery can charge in just 3 minutes. We want to know if it will charge in 3 minutes, if it's exactly 3 minutes to charge it. Not will it be 3 minutes or more, not will it be 3 minutes or less. We want to know if it charges in 3 minutes. So we want to know if the average amount of time, we want to know if mu, right? What is our HO, right? The null hypothesis is what we're testing. It's our suspicion. We want to know if the average amount of time it takes to charge this battery is exactly, or if it's equal to 3 minutes. That's what we want to know. Will the average be exactly 3? Against the alternative hypothesis, right? We know step 1, right, from our previous lesson, we know that if we have an equal to sign in the null hypothesis, if we have an equal to sign here, then we have a not equal to sign in the alternative hypothesis. And if we have a not equal to sign, then we're saying, all right, well, you know what? We want to know if it's going to be equal to 3 minutes, but maybe it's not equal to 3 minutes. That's the opposite, right? Okay. Well, that information tells us that we have what type of test? We have a two-tailed test, right? We have a two-tailed test because we have a not equal to sign in the alternative hypothesis. We have a two-tailed test, which means that we have a positive critical value over here, and we have a negative critical value over here. Okay, this is the negative critical value because it's to the left of 0. We have a positive critical value because we are to the right of 0. So we know that we have a two-tailed test. Okay. So the rest is fairly straightforward, right? I mean, I said, let's do step 2. We'll put that up here, right? We'll do step 2, step 3, and step 4 all here. But I said in the setup of the problem, they're like, all right, well, we just invented a rechargeable car battery that fully charges in only 3 minutes. We want to know if it's reasonable to think that our new battery charges in only 3 minutes. We take a sample of 11 batteries. So we have 11 batteries, and we discover that on average, they charge in 2.85 minutes with a standard deviation of 0.42 minutes. At the 0.05 level of significance, is it reasonable to believe the new car battery charges in only 3 minutes? All right, well, 0.05 is the level of significance, okay? Step 2, determine the level of significance. Okay, well, done. It's already there. 0.05. Okay, done. Move on to step 3. Step 3 is choose the formula for your test statistic. Okay? In other words, I'll even scroll back to the step here, right? Step 3, determine the formula for our test statistic. The one and only question that we ask ourselves is, do I know the population standard deviation, right? If the answer is yes, if we know the population standard deviation, we're going to work with this formula. And if the answer is no, we're going to work with this formula. Okay, well, do I know the population standard deviation? Let's go back to the question. Okay, it says, I want to know if our new battery, our brand new battery that has never existed before, I want to know if they will charge in 3 minutes. So I find out that the standard deviation is 0.42 minutes. I'm just going to clean up that 2 here. Okay. So this brand new battery, there's only 11 of them in existence. It's brand new. So I want to know, do I know the population standard deviation? Well, here, the standard deviation, it doesn't say population or sample, but guess what? If this is a brand new battery, right, if there's only 11 of them in existence, then the standard deviation, this would be a population. That would be the population standard deviation because it's brand new. There's only 11 of them out there. So this is the whole set. Okay, if that's the whole set, then that's it. That's the population standard deviation. The population standard deviation is 0.42 minutes. So we have to choose our test statistic formula. Do I know the population standard deviation? Yes, I do. So my test statistic formula, my t-stat, is going to be equal to x bar minus mu over sigma divided by the square root of n. Okay. Step 4, critical values. Okay. In order to get the critical values, I need 3 things. I need to know if I have a 1 or a 2-tailed test. I have a 2-tailed test. I need to know alpha, the level of significance. Well, alpha is 0.05. And I need to know the degrees of freedom. Degrees of freedom is n minus k. Okay. So n is my sample size. What's my sample size? My sample size is 11. I took a sample there. How many things are in my sample? 11 of them. I took 11 things in my sample and I determined, and so that's 11. That's n. My sample size is 11. Since my sample size is 11, I have 11 observations in my one sample, which means that I have 10 degrees of freedom. Right? So in order to get my critical values, I have a 2-tailed test, 0.05 level of significance, and 10 degrees of freedom. At that point, I'll go get the critical value. Okay. So I have a confidence interval, level of significance 1-tailed, level of significance for a 2-tailed test, right? 2-tailed test, 0.05, 10 degrees of freedom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 degrees of freedom. 2-tailed test, 0.05, right? 10 degrees of freedom, 2.228, right? 2-tailed test, 0.05, 10 degrees of freedom, that's 2.228, which means I have plus minus 2.228. Okay, that's my critical values. So just to kind of round out my graph here, Remember, I have a negative critical value, negative 2.228, and I have a positive critical value of 2.228. Okay. So at the end of the day, what's a hypothesis test? A hypothesis test is nothing more than comparing the test statistic against a critical value. You're comparing the test statistic against the critical value, which means if my test statistic, if the result of this formula, if it goes past either negative 2.228 or positive 2.28, then in other words, if it goes past it, if it goes into here, I will land in the region of rejection. It will land in the region of rejection. If I go past it, if I land in the region of rejection, I will reject the null hypothesis. I will end up, crossing this out, right? On the other hand, if my test statistic does not go past negative 2.228 or positive 2.228, if I don't go past it, then my test statistic lands in the region of non-rejection. And if I land in the region of non-rejection, then I will fail to reject the null hypothesis. If I fail to reject the null hypothesis, I will say, you know what? Yeah. I think it's reasonable to think mu is equal to 3, right? It's reasonable to think that the average amount of time to charge this car battery is 3 minutes. All right, so let's see the result. What's step 5? Step 5 is go, actually do the problem. So I need to get my test statistic. I need to plug in the data. So I have an average of 2.85, that's X bar, 2.85, standard deviation is 0.42, and 11 batteries, okay? So 285, 42. Okay, so we have 2.85 for X bar minus 3.00 divided by 0.42 over the square root of n, right? Square root of n is 11. Okay, so where am I getting this from? I'm getting it from the problem, right? I mean, X bar, I said on average, the batteries lasted, my sample average was 2.85 minutes. That's how long it took to charge. So that's a sample mean, that's 2.85. Mu is 3. That's what I'm interested in. I want to know, is mu 3? I'm testing that. So is mu 3? Population standard deviation? I said yes. I said yes. I do know the population standard deviation, and that standard deviation is 0.42. And then my sample size is 11. I tried 11 batteries out. Okay. So where do I start? I start in the denominator. Okay. I start with the square root of 11. Square root of 11 is 3.31. Okay, and I can, in the numerator, I could do this as negative 0.15. Okay. I'm just adding in these parentheses here, the brackets. Okay. The next step, I'm going to do 0.42 divided by 3.31, which gives me a denominator of 0.13. I'm rounding up. The answer, the denominator, 0.42 divided by 3.31 is 0.126. I made 0.126 into 0.13. And then my numerator is negative 0.15. Okay. Then finally, negative 0.15 divided by 0.13 gives me a test statistic of 1.15. Okay. This is my test statistic. So what's the results? What happened? All right. Well, my test statistic is 1.15. 1.15 on a number line. 1.15 lands right here. 1.15 puts me in the region of non-rejection. Okay. This read, right? 1.15. It didn't go past 2.228 or negative 2.228. Didn't go past this. 1.15 is right in here. Okay. It's in the region of non-rejection. If your test statistic is in the region of non-rejection, then you fail to reject the null hypothesis. Okay. We fail to reject it. We're basically saying this. We're failing. We're like, yeah, all right, right? We're failing to reject. We're accepting it. We're not really accepting it, but we're failing to reject it, right? If we fail to reject the null hypothesis, then we're saying it is reasonable to think or to believe the battery charges in 3 minutes. Okay. And then we're done. That's, well, almost. We still have to get the p-values, but okay. That's it. Our test statistic, right? The test statistic 1.15. 1.15 is right here. That falls into the region of non-rejection. I am just messing this up right there. Let me erase that. Okay, we're in the region of non-rejection. Okay. And if we're in the region of non-rejection, then what we do is we fail to reject the null hypothesis. If we fail to reject the null hypothesis, then it's reasonable to think, reasonable to believe that the battery will charge in 3 minutes. Okay. So how confident are we in our results? In other words, like, yeah, no, it's going to take 3 minutes to charge the battery. It takes 3 minutes to get it. That's what's happening. It takes 3 minutes to charge it up. Okay. And then somebody comes in and says, "Are you sure?" You go, it's a new battery, but I'm sure. I mean, this is what happened. And go, "Are you sure? Sure?" You go, I think so. You don't want to say, "I think so." You want to say, "Yeah, I know so," because the p-value is blank. Okay. And that's where the p-value comes in. The p-value tells you how confident you can be in your results. Okay. So let's see how we can get a p-value here. Okay. In order to get a p-value, we'll do step 5b. Okay. There's 2 formulas for a p-value, depending upon how many tails you have. Okay. So if you have a 2-tailed test, p-value is equal to 2 times 0.5 minus the area associated with the test statistic. Okay. So if you have a 2-tailed test, what you have to do is you have to You have your test statistic, right? Ours was 1.15. You have the area of you have the test statistic of 1.15. You then need to get the area associated with that test statistic. You get the area associated with the test statistic, 1.15. Let's say whatever the area is, okay? Once you get that area, you do 0.5 minus the area, and then 2 times that, okay? So let's see how this works out, what we do, okay? Our test statistic is 1.15. So this is equal to 2 times 0.5 minus the area of 1.15. Okay. We need to get this area. We need to find the area. We need to find the area of the test statistic equaling 1.15. How do we do that? We go to the z distribution. We go to the z distribution. And when we go to the z distribution, again, 1.15 can be broken down. 1.15 can be broken down into 1.1 and 0.05. So we have 1.1 and 0.05. Okay, 0.05. 1.1 and 0.05. That gets us an area. That gets us an area of 0.3749. Okay, so when we're getting our p-values, right, whatever your test statistic is, you have to get the area associated with the test statistic. How do you do that? To get the area, you go into the z distribution. Once you're in the z distribution, take your test statistic, whatever your test statistic is. Ours is 1.15. So take that 1.15 and go 1.1, 0.05, match it up. 1.1, 0.05, 0.3749. Okay, 0.3749. That is your area. That's the area associated with the test statistic, 0.3749. So we are then going to plug that into our equation. Okay, equals 2 times 0.5 minus 0.3749. Where did I get this 0.3749 from? That we had a test statistic of 1.15. I then went to the z distribution and I looked up 1.15 in the z distribution. That gave me an area of 0.3749. Okay, so now, very simply, I just start with the brackets. I'm going to do 0.5 minus 0.3749. Oops, that was which is which gives me 2 times 0.1251. And then if I multiply that by 2, that gives me a p-value of 0.2502, which is approximately equal to 0.25. Okay. So now we're going to figure out how to interpret this. The interpretation is key. My p-value is approximately equal to 0.25. Okay. When you are doing p-values, you always compare the p-value to alpha. Okay. Always compare the p-value to alpha. If p is greater than alpha, if p is greater than alpha, you fail to reject the null hypothesis. If p is greater than alpha, you fail to reject the null hypothesis, and you are very confident in your results. Okay, you can be very, very confident in your results. If p is less than alpha, then reject the null hypothesis. Okay, so if p is less than alpha, then you reject the null hypothesis. And that is the rule for p-values, okay? The bigger and bigger and bigger that p gets in relation to alpha, the more confident you are in failing to reject the null. Okay? The more confident you are in failing to reject the null. That's what's going to happen here, by the way. Okay? But if p is less than alpha, okay, the smaller and smaller and smaller that p gets, especially in relation to alpha, the smaller that p gets, the more confident you are in rejecting the null hypothesis. Okay, so in other words, if p is 0, right? I mean, that's the smallest it could be because p stands for probability. So if p equals 0, then you absolutely reject the null hypothesis. You say, there's no way this is correct. Nope, nope, nope. Reject the null hypothesis. But on the other hand, if p is greater than alpha, then you will fail to reject the null hypothesis. Okay? You would fail to reject the null. The larger and larger the p gets in relation to alpha, the more confident you can be in failing to reject the null. So let's go back to our example here. Okay? P was approximately 0.25. Okay? From our question, alpha was 0.05. If you don't remember that, it is from the scenario right here. Okay? We just invented a rechargeable car battery, fully charges in only 3 minutes. We want to know if it's reasonable to think it charges in 3 minutes. We take a sample. So at the 0.05 level of significance, is it reasonable to believe the new car battery charges in only 3 minutes? That's what we want to know. We want to know, is it reasonable to think that it'll charge in only 3 minutes at the 0.05 level of significance, right? So we did this whole hypothesis test and we said, you know what? Okay, 1.15, right? 1.15, that test statistic does not go past the critical value, doesn't go past the critical value. So we are in the region of non-rejection. We're in the region of non-rejection. So I fail to reject the null hypothesis, right? I fail to reject the null. It is absolutely reasonable to think that the battery charges in just 3 minutes, right? I put the check mark up here. It says, yep, battery's going to charge in 3 minutes, right? And then your boss comes along and says, hey, so I heard that you're doing the hypothesis testing for the battery charges, right? You're doing the testing to figure out, is this thing really going to charge in 3 minutes? And you say, well, yeah, I ran the hypothesis test and it does. I failed to reject the null hypothesis. And so, yeah, I do think it's going to charge in 3 minutes. I really, really do. And then your boss says, how confident are you? You go, well, I'm pretty confident. I ran the hypothesis test and I think it's going to charge in 3 minutes. Sure. And then you say, how confident are you? And then you could say, you know what? I'm very confident because in this instance, you could say I'm very confident, right? I'm very confident because P is 0.25. Alpha is 0.5. So P is greater than alpha. P is great. In fact, it's about 5 times bigger than alpha, right? 0.05 times 5, you get to 0.25, right? So it's 5 times the size of it. That's like if that's like if one football team, right? Or take soccer, right? International game. If one team gets 5 and the other team gets 1, that's considered a blowout, right? That's 5 times more than what the other team got. If a soccer game ends 5-1, or a football game to the rest of the world, right? If that ends 5-1, the team that got 1 goal never stood a chance. They weren't in the game. They got blown out, right? So that would mean that the team that got 5 was dominant compared to the team that got 1, which means that in this example, if P is 5 times the size of alpha, that means that P is very dominant compared to alpha. In other words, P is greater than alpha, and it is much, much, much greater than alpha. If P is greater than alpha, fail to reject the null hypothesis. So we fail to reject the null hypothesis. Okay? Therefore, your boss comes along and says, hey, I noticed you're doing the hypothesis testing for the rechargeable car batteries, right? Okay. So yeah, we're in the region of non-rejection, right? We fail to reject the null hypothesis. Yeah, it's reasonable. It's reasonable to think that the battery charges in 3 minutes, right? That's reasonable. How confident are you in your decision? And you say, I'm very confident because P is much, much, much greater than alpha. P is much greater than alpha, so I am very confident in failing to reject the null hypothesis. Therefore, I am incredibly bullish on the idea that this car battery will charge in exactly 3 minutes. I believe that. I think it's safe to market, right? You would say, I think you should advertise this car as it charges its electric battery faster than it takes to fill up a tank of gas. And then that car, in theory, right, people will run out to go buy it because not only is it electric, but it charges even faster than it takes to get gas. Well, if it charges faster than it takes to fill up on a gallon of gas and you don't have to pay for gas anymore, then what will end up happening is, theoretically, that car will sell quite well. So you would say, yes, I am very, very, very confident in my car battery's ability to charge in just 3 minutes, because not only did the hypothesis test told me that I should fail to reject, the hypothesis test told me that it's reasonable to believe that, right? That's what this says. The actual hypothesis test says, yeah, it's reasonable to think that the car charges in 3 minutes. And then the p-value told you, yes, you can believe that. You can believe it. It's going to happen. Okay. That you can be very confident in that. Okay. Because p is 0.25 and alpha is only 0.05. Okay. So that is one example. That's a two-tailed test, right? That is an example of a one sample hypothesis test that just so happened to be a two-tailed test. Okay. And then we included the p-value with it. Okay. I mentioned there's two formulas for a p-value. If you have a two-tailed test, then this is your formula. Okay. Now we're going to do a one-tailed, now we're going to do another hypothesis test. We're going to do another one sample hypothesis test. Spoiler alert, it's going to be a one-tailed test, right? Because then we will do the entire hypothesis test with a one-tailed test, and then I will do the p-value at the end of it. I'll do the p-value at the end of it, and I will show you the p-value, the formula. I'll show you the formula for the p-value, what happens when you only have a one-tailed test, okay? What do you do when you have just a one-tailed test for a p-value? Again, spoiler alert, guess what? If you have a one-tailed test, you just cross out the 2. That's it, okay? When you're calculating the p-value for a one-tailed test, right? Formula for, 2 formulas for p-value. If you have a two-tailed test, you have to multiply it by 2 because you have 2 tails. But if you have a one-tailed test, this is your formula right here. You would just eliminate that 2, okay? But we're going to do it from the top, okay? We're going to do a one-sample hypothesis test, which is going to be a one-tailed test. And that means that we will have to calculate the p-value for a one-tailed test. Okay, so that's the next thing we're going to do. So let's say now we work in, let's say real estate. We work in real estate. And let's say we want to know if the average price that I could, let's say we work in real estate, we're thinking about building a new condominium building, okay? Thinking about buying new condos. And I want to know if the average price that I could sell each one of these condos for, each of the new condos in my new building, I want to know, I'm going to build a new building. Okay. I want to know if, let me clean up this handwriting a little. If each new condo unit can sell for $1.25 million or more. Okay. I want to know if it can sell for 1.25 million or more. To do so, I examine the last 12 deals the last 12 condo deals or sales, right? And to discover that the average sale price is, let's see, sorry, I'm just thinking here. The average sale price is $1.12 million with a sample standard deviation with a sample standard deviation of $328,000. at the 0.05 level of significance, determine if it's reasonable to believe the new condos can sell for $1.25 million or more. Okay. So what we want to do is we're going to build a condo building. We want to know if each one of these new condos can sell for $1.25 million or more. So to do so, I'm looking at the last 12 deals or sales in the area, right? The comps, right? The last 12 condo deals or sales in the area with, similar bedroom, bathroom setups, right? Excuse me, to discover that the average sale price of the last 12 deals is $1.12 million with a sample standard deviation of $328,000. At the 0.05 level of significance, I then want to determine whether it's reasonable to believe the new condos can sell for $1.25 million or more. Okay, so what do? Step one, state the null and the alternative hypothesis. What do I want to know? I want to know if I can build a new condo and if I can sell each unit for 1.25 or more. So I want to know null hypothesis, right? What am I trying to figure out? I want to know if I can sell these condos, if the average sale price will be greater than or equal to $1,250,000 or more. I want to know if the average sale price is going to be greater than or equal to 1.25 million, right? I want to know, hey, all right, I'm going to build all these new condo units. Can I sell each one of them for 1.25 or more? 1.25 is $1,250,000. So I want to know, can I sell it for greater than or equal to $1,250,000 against the alternative? If mu is less than $1,250,000. Okay. So right off the bat, I immediately know I have what type of test? Well, I have a one-tailed, left-tailed test. How do I know that? I'm looking at my alternative hypothesis. In the alternative hypothesis, I have a less than sign. The less than sign is pointing left. Okay. Since it's pointing left, that means that I have a one-tailed, left-tailed test. Which also tells me that I have a negative critical value. Okay. So I have a one-tailed, left-tailed test. Step two, level of significance. The level of significance was 0.05. We could just move right on from there. That's what I said. I said it right in the setup, right? I want to know at the 0.05 level of significance. Okay. So I then move on to step three. Step three is choose your test statistic formula. Okay, test statistic formula. There is one and only one question you ask yourself when you are trying to determine the formula for your test statistic, and that is, do I know sigma, right? Do I know the population standard deviation? Well, the answer here is no, I don't. I don't know the population standard deviation because it says sample standard deviation, okay? And to be honest with you, if it didn't say sample standard deviation, right? If it just said $1.12 million with a standard deviation of 328, well, you should still know that that would be a sample standard deviation because this isn't going to be the only condos that have ever sold in the history of, real estate, right? Condos have been sold for a very, very long time. And so, this sample, this building going up isn't going to be the only time that ever happens. So that's not the population, that would be the sample, right? So my test statistic formula is going to be X bar minus mu over S divided by the square root of N, right? Step 4, critical values. Okay. In order to get the critical values, we need 3 things. We need to know if it's 1 or 2-tailed. It's 1-tailed. We need alpha, which is 0.05. And then we need the degrees of freedom. The degrees of freedom, n minus k, right? Well, n, how many other deals did we look at, right? For n, we looked at the last 12 deals or sales. We looked at 12 of them, which means we have a sample size of 12. We have 12 observations. K is the number of samples. How many samples did I take? I took 1 sample. I did this 1 time. It's also a 1 sample hypothesis test, but I took 1 sample of 12 observations, and that gave me 11 degrees of freedom. Okay, 11 degrees of freedom, 1-tailed test, 0.05, and that will give me, within my t distribution, right? I have to go down to the t distribution. So I have a 1-tailed test, 0.05 level of significance, right? 0.05, 1-tailed test, 0.05, 11 degrees of freedom, right? 11 degrees of freedom for a 1-tailed 0.05. 11 degrees of freedom is 1.796. Right? 1.796 is my critical value because I did a 1-tailed test, 0.05, 11 degrees of freedom, 1.796. So then remember, I have negative 1.796 because I have a 1-tailed left-tailed test, right? Since I have a 1-tailed left-tailed, I am past 0. Zero's in the middle. Since I'm to the left of 0, I have a 1-tailed left-tailed test. Okay. And then the only thing left to do is go, right? Actually do the problem. Okay. So my test statistic is going to be equal to X bar, right? Minus mu over S divided by the square root of N. Okay. If we want, we could put this in brackets too. No big deal. We put in brackets. So that means that my test statistic, what's X bar? What's the average? X bar is the average that I saw these other sales being sold for, right? The average sale price of these other deals was $1.12 million. Okay, the average sale price was $1.12 million. So my T-stat, if I'm going to do X bar, the average price was $1.12 million. So that is $1,120,000 minus mu. What's mu? It's 1.25, right? That's $1,250,000 divided by S, right? It's the square root. The standard deviation of the sample, was 328 I just want to make sure. I believe that number is right. I'm just double checking what I wrote. 328,000. Yep. So again, 1.12 minus 1.25 over $328,000 divided by the square root of n. What's n? It's 12. Okay, that's my sample size. I looked at the last 12 deals. Okay. And now I just have to do a straightforward calculation. What is the square root of 12? Square root of 12 is 3.46. Okay. I can keep these brackets here if I want to. I can do the numerator, right? 1.12 minus 1.25, or $1,120,000 minus $1,250,000 is negative $130,000. Come on. Okay. Which is equal to negative 130,000 over 328,000 divided by 3.46 is 110,404. And therefore, my test statistic is 1.18. Oh, sorry, negative one. Let's see if I can squeeze this in here. Equals negative 1.18. Okay. Because it's right, the numerator is a negative, the denominator is positive, so this is going to be a negative number. So my test statistic, negative 1.18. So on a number line, 0, negative 1.18 does not get to negative 1.7. Okay. It's over here, negative 1.18. Okay. So since negative 1.18 is in the region of non-rejection, so the region of non-rejection, and therefore I fail to reject the null hypothesis. Okay. I should probably write that out for you. Fail to reject the null hypothesis. And therefore, it is reasonable to believe condos will sell for $1.25 million. Okay. So in other words, my test statistic, I'm in the region of non-rejection, right? I'm in the non-shaded region I'm in the region of non-rejection. So since I'm in the region of non-rejection, I fail to reject the null hypothesis. I fail to reject it. I think it's a good, I'm in the region of non-rejection. I fail to reject. If I fail to reject the null hypothesis, then I think it is reasonable to believe that these condos will sell for 1.25 million or more. Okay? That's what I'm saying. I think it's reasonable to believe that. Okay? Now, construction, real estate, these are big capital projects. These are expensive things. When you put up a building, it's there for a long time. So people really want to know. They have a huge interest in making sure that when you say, yeah, you can sell these new condo units for 1.25 million each, and they say, are you sure? You say, yes, absolutely. You could sell this for 1.25 million. And they say, how sure are you? And you say, well, have you seen the p-value? Okay. That's where the p-value would come in, because you would say, yes, it's reasonable to believe that you can get 1.25 million for each of these units. And I checked the p-values, and the p-values are solid. Let's see how we calculate those now. Okay. The p-value, as I said earlier, the p-value for a one-tailed test Okay. The p-value for a one-tailed test is just 0.5 minus the area associated with the test statistic. Okay. If we had a two-tailed test, right? Just I'll put this right here, right? If it's two-tailed, if it's a two-tailed test, then P is equal to 2 times 0.5 minus the area associated with the test statistic. But you know what? We don't have a two-tailed test. We don't have a two-tailed test. We have a one-tailed test. So this is going to be our formula. Our test statistic was 1.18, I believe. Let's check. 1.18. Yeah, negative 1.18. So our test statistic is negative 1.18, which means we need to do 0.5 minus the area associated with a test statistic of 1.18. We need to, right? This means we need to get the area. So we go to the Z distribution. Okay. So let's go to the Z distribution. Our test statistic is 1.18. When we go to the Z distribution, our test statistic of 1.18 can be broken down into 1.1, 1.1, and 0.08. 1.1 and 0.08. 1.1 and 0.08 gives us 0.3810. Okay, we don't need to make this negative either. There's no such thing as negative area. You can have negative z-scores, negative test statistics, or negative anything. You cannot have negative area. The concept of negative area is meaningless, right? So we have negative 1.18 for our test statistic. So that's 1.18. And we have area of 0.381. 0.3810. Okay. So now we have an area. We have 0.5 minus 0.3810 for our p-value. P is equal to, oh, I should just do this in my head. 0.5 minus 0.3810 is 0.1190. Okay. So the p-value, p is 0.119. Okay. Alpha, just to remind the viewer, right? Alpha was 0.05. Okay. So since p is 0.119 and alpha is 0.05, this is telling us that p is greater than alpha. Okay, p is greater than alpha, and it's much greater than alpha too. So if p is greater than alpha, we fail to reject the null hypothesis. Okay. We fail to reject the null hypothesis. And so therefore, if we go back to the setup again, right? So then we would say, all right, well, you know what? Great. I want to know if I can sell these condos, right? I'm going to build this new condominium building. I want to know if I can sell each one of the units for $1.25 million or more. Can I do that? Is that even possible? And then you say, you know what? All right, well, I ran the numbers and it turns out that, the test statistic falls into the region of non-rejection. Since the test statistic falls into the region of non-rejection, it is reasonable to believe, right? It falls into the region of non-rejection. So I'm going to fail to reject the null hypothesis, right? I'm going to kind of put a check mark by this, right? I fail to reject it. Since I fail to reject the null hypothesis, I think it's pretty reasonable, actually. I think it's reasonable to believe that you could sell a new condo unit for 1.25 million. I think each one of those could be sold for 1.25 million dollars. Oh, well, that's great. That's wonderful news, right? How confident are you? Right? How confident are you? So it's reasonable to think I could sell these condos for 1.25 million. Are you sure? And you say, yeah, actually, I'm sure. I mean, I looked at the p-value, right? And the p-value for these, the p-value is 0.119. Okay. Alpha was only 0.05. So p is much, much greater than alpha, right? P is much greater than alpha. And we know, right? We know over here that if p is greater than alpha, right? If p is greater than alpha, then we fail to reject the null hypothesis, right? If p is greater than alpha, fail to reject the null hypothesis. On the other hand, if p is less than alpha, we would reject, but that's not the case right now, right? What we know is that p is actually greater than alpha, right? P is greater than alpha. P is 0.119. Alpha is 0.05. So P is greater than alpha, and therefore we fail to reject the null hypothesis. And therefore, I'm very confident. I'm very, very confident that I could sell each one of these new condo units for $1.25 million or more. I think so. So let's break some ground, right? Let's go build this building. Okay. So that's how we would use that's a one sample hypothesis test. That's a one-tailed one sample hypothesis test. Okay. So just sort of to wrap this all up, right? We have confidence intervals, which creates a range of values likely to contain the mean. So it's a range. We have the lower bound and the upper bound. Okay. And then we have hypothesis tests. Hypothesis tests are trying to figure out if it's reasonable to believe a hunch or a suspicion. A one sample hypothesis test is testing your hunch, your hypothesis, your suspicion against a specific value. And a two sample hypothesis test is comparing your hunch or your suspicion against a different population. We didn't get there yet. We will, but in coming chapters, but not yet. Okay. But that's the point of it, to compare your population against another population. You don't really care about the values as much as you just care about the relationship between the two values, the two populations, excuse me. But now, for the one sample hypothesis test, what we did is compare the population against a specific value, right? We tried to find out, if the battery charges in 3 minutes, if the price of Home Depot is $75 or more, if the plane will get to California in 5.5 hours or less, if I could sell these condo units for $1.25 million or more. That's the point of a one sample hypothesis test, is you're comparing a test that, excuse me, you're comparing the population against a specific value. Now, when you're comparing the population against a specific value, right, that's a one sample hypothesis test, you can have a one-tailed test or a two-tailed test. A two-tailed test I'm trying to pull up the whiteboard here. A two-tailed test would mean that you have an equal to sign and a not equal to sign in the null and the alternative. Okay, and that's the point of a two-tailed test. Two-tailed test has a not equal to sign. But then you could also have a one-tailed test. You could have a one-tailed left-tailed test, or you could have a one-tailed right-tailed test. And with those one-tailed left-tailed or one-tailed right-tailed test, what you're trying to do is figure out, all right, well, is the stock price $75 or more? Against the alternative, is the stock price less than $75? Okay. Or you could be trying to find out, is the stock going to be $75 or less against the alternative greater than 75? Okay. But that's what we're doing here with one sample hypothesis test, right? One sample hypothesis test, you are comparing the population against a specific value. And then what we are doing is we are trying to figure out if we have a one-tailed test, like we do here, or a two-tailed test, like we do here. And we're trying to do that. We're trying to figure out if we have a one-tailed or a two-tailed test, because at the end of the day, we are going to determine if the test statistic goes past the critical value or if the test statistic does not go past the critical value. If the test statistic goes past the critical value, then you are in the rejection region, the region of rejection, which means you should reject the null hypothesis. You should get rid of it. Okay, you should say it's unreasonable to think that these condos could sell for 1.25 million or more, or it's unreasonable to think that the stock price is $75. On the other hand, if the test statistic falls into the non-shaded region or the region of non-rejection, then you fail to reject the null hypothesis. If you fail to reject the null hypothesis, then that means it's reasonable to think, whatever your hypothesis is, right? It's reasonable to think that your suspicion or your hunch about the value is correct, right? Your specific value, your hunch about that, it's reasonable to think that that is correct. And therefore, you would say, I failed to reject the null hypothesis, and therefore, I'm on the right track, okay? Lastly, how confident can you be in your results? That's the whole point of the p-value, okay? The whole point of the p-value is to determine how confident you can be in your results. If you have a one-tailed test, let's go to this one, sorry, wrong whiteboard, right? If you have a one-tailed test, okay, if you have a one-tailed test, this is how you would calculate the p-value. P-value for one-tailed test. And if you have a two-tailed test, this will be your formula. Okay? With the difference just being you multiply it by 2, right? 0.5 minus area test statistic, 0.5 minus area of the test statistic. You multiply this by 2. This doesn't get multiplied by 2 because this is a two-tailed test and this isn't. Okay? But the p-value tells you how confident you can be in your results. You calculate it using these formulas. And then once you calculate the p-value using those formulas, you simply compare it to alpha. If your p-value is greater than alpha, then you fail to reject the null hypothesis. If your p-value is less than alpha, then you would reject the null hypothesis. And that is one sample hypothesis testing. And frankly, that is how hypothesis testing works. Okay? All hypothesis testing involves or revolves around state the null and the alternative, determine the level of significance, get your determine your formula for your test statistic, determine the critical values, and then actually calculate the test statistic, compare it to the critical values, get the p-value, see how confident you are. That's it. There's a lot of moving parts to it, but at the end of the day, you're really just comparing a test statistic against a critical value to see if you land in the region of rejection or the region of non-rejection. And then you want to get the p-value to see how confident you are in your results. And that's all there is to it. Okay, so that concludes one sample hypothesis tests. The next thing we're going to do is two sample hypothesis tests. As you'll see, there's really not much to change for the two sample hypothesis test. Okay, we're going to swap out a number for another population, right? We're not going to try to, we don't care if the average income of Jersey City is $100,000. We don't care about that. We just want to know, is Jersey City richer than Hoboken, right? And then, so we're just going to swap out a number for a second population. And then what we're also going to do is we're no longer going to be calculating these by hand because the formulas, step 3, right? Determine your test statistic. The formulas for the test statistic can start getting a little bit bigger, a little bit messier. You can do it by hand. It's really not hard. I mean, you can do it. You can just look it up online, how to, the formulas for a two sample hypothesis test. But honestly, people run them on computers all the time. That's where you will be doing it, right? I would be hard pressed to believe you'll be doing it by hand. So instead, we're going to learn how to do it on computers and then interpret it by looking at computer screens. And that's the point of the next lesson, which is two sample hypothesis tests. So we'll pause there and we'll pick it up again when we actually start doing two sample hypothesis tests.